All right, ladies and gentlemen, greetings. We are going to begin a new section, section 7, on computer memory system. And this is a very important aspect of computer organization and design, because no matter the speed of your processor, if we cannot, design a memory system that matches, of course, at the moment, the match is not perfect, but the idea is to design a memory system that steps up to the performance of your processor, so that the overall performance of your computing system is not bottlenecked by memory. So this is the outline of what we intend to cover. An introduction, the practical technologies that are available in the industry to build memory, and how those are, composed together to actually realize practical memory systems that are similar to the ones we find in our, computing devices, either your phone, your desktop, or even a server. And then speak a bit more closely regarding cache memory, which is an important aspect of trying to, build that memory solution that is closer to the speed of the processor as much as possible. All right. So this is just a recap of something that we covered previously, highlighting how the operation of a computer system really, in basic terms, is defined by the interaction between your processor and your memory. Your processor being the master, meaning it issues requests or commands, and then your memory being the slave. It responds to the processor's requests. So the processor performs computations, be it addition, subtraction, multiplying, and then memory provides storage facility, for those instructions that we want the processor to consume, or for the data that is generated as results by the processor. So we have this interface between the processor and memory, which is a bus that is used by the two to communicate, to issue commands, and to actually transfer data, between the two. So one important point really here is that it is very important that this highway between your processor and your memory is made as fast as possible, so that the access time, meaning the time it takes for the processor to receive a word that it requested from memory, is kept as minimal as possible. Both, of course, are clocked, meaning they respond to changes in the CPU clock. So memwrite, the processor can either want to write to memory, and therefore it will set that to 1. It wants to read, set that to 0. It specifies the address that it wants to write or read from or to, and the data it wants to write, or the data that it wants to retrieve from memory into its own internal processor storage made up of registers for processing, right? So really, good design principles should be applied to achieve a memory system with good performance. This is the object of this topic or this lecture, and to look into those various technologies, techniques that are used to bring memory up to speed, so that it can work well with the processor to perform the functions that a computer ought to support. So ideally, if wishes were horses, this is what the processor would like to have from memory, right? Of course, wishes are not um, horses, right? So there are trade-offs that ought to be made in life, because we don't always get the ideal things that we want. But ideally, the processor would love to have memory that is cheap, at the same time high speed, same time high density, meaning we can store more bits per unit area. Don't want to have a big chip for you to get, large capacity. Non-volatile, meaning it can persist, meaning store permanently what we write to it. It can support reads and writes, and it's not power hungry. Okay, it uses energy efficiently, especially important in our mobile computing domain, where you are worried about issues such as your battery life. So the processor ideally would love memory to be very easy on 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 the energy, and then durable. It should not break after a couple of years usage, and it should be removable. Okay, be able to plug it in one device, plug it out, and put it on another device and still have it working and be able to access the data that you stored on it. Of course, this can be realized by different um, memory technologies, okay, but not one, okay, not one. Of course, in principle, it's possible to have a very high speed, high density. Yes, but the moment you bring all the requirements into one solution, then of course you have the cost skyrocketing as well. So we will see how computer architects, use the concept of hierarchy to try and provide an illusion of one memory system that uh, meets all of this requirement. So this is just highlighting what we just discussed now, which is the idea that memory is a big issue. Okay, optimizing its performance to step up to the performance of your processor has always been a big problem, and it actually bottlenecks the performance of your computing system. So computer systems tend to require much more code and data storage than computational hardware. Okay, so in terms of hardware, building a processor that is fast and ALU that can, perform multiplication faster, of course, it becomes expensive. It becomes expensive as well in terms of, the area that it is going to require on your die, your IC. But the hardware aspect of computing is not really a main challenge. The main challenge also, is with regards to building memory systems that are fast, that provide a good persistence of data. We have highlighted this, that CPUs have increased in speed more rapidly than memory devices. Obviously, what happens? They have to, slow down. They are slowed down by memory. So we need to come up with techniques that deal with this processor memory performance gap, so that we have a faster computer. have a faster computer. Of course, the techniques which are employed and their complexity and even the cost tax attached to them will differ depending on the kind of computer you're building. We have computers for mobile computing. They have different architectural requirements to computers for desktop computing, computers for server computing, so on and so forth. But the problem remains the same. It's just that techniques and technologies applied in each context will differ, and the cost implications will also differ. So practically, what memory technologies do we have? What are their advantages? What are their cons? And then subsequently, how can those be cooked together, right, into one memory solution made of multiple memory ingredients, right, to provide a unified hierarchical memory solution. So this is an overview of computer memory classified in terms of either it's internal or external. Internal, meaning how it is directly connected to your processor. External meaning it's not directly connected to your processor. There is a controller between your processor and that specific memory technology. So internal memory, or often referred to as your main memory, includes things like your ROM, which is used on computing devices, for example, to store to store manufacturer specific configurations for your phone or for your laptop. For example, the code that loads like that boots up your phone, right? We stored in ROM, bent in ROM by the manufacturer of your phone. Then you have RAM as well, which is volatile. You write to it, you power it off, it loses what you wrote to it. And it also has multiple classes. The more faster one, your SRAM, built from flip-flops compared to your DRAM one, built from capacitors. And of course, DRAM has variations also, SDRAM, RDRAM, DDR, EDR, SDRAM, just with one goal of trying to enhance performance and get a faster, cheaper memory solution. This is like double data rate, SDRAM from 1, 2, 3, 4, with one having a lower data rate and 4 having a higher data rate, meaning you can pull more data from that memory at the same time and faster. Then we have the external one, which we said has a controller between the processor and that storage, managing the storage. This includes your HDD, your SSD, which is faster than your HDD. Of course, it's more expensive. Your compact discs and your flash drives and other secondary, external permanent memory solutions. Okay, this is an overview in terms of access time, which is very important, especially in this discussion of trying to make sure that memory steps up to the performance of your processor. One measure which is used today is access time. How quickly does memory respond when the processor has sent a request for a word? So depending on the technology used to build that memory, then we have a varying degrees of access times for your SRAM. This is your static RAM, built from flip-flops, and it's faster. But of course, this is the same technology which is used to build like to build your registers. And so it's faster than your DRAM. DRAM is faster than flash, which is faster than magnetic disk. But of course, the price tag also, is inverted, with the faster being more expensive, obviously. So this is DRAM. We have already introduced it, that this is dynamic and random access memory built using a capacitor, meaning the single memory cell, which is used to store 1 bit of data, achieves that through a capacitor. So when the capacitor is charged fully, then you have a 1 written to that cell. When it discharges, or when it is discharged, then you have a 0 stored in the cell. This is easy to set up. It's cheaper, also because of the price tag of your capacitors. The only issue really here is that capacitors naturally leak charge, so they constantly have to be refreshed or recharged to make sure that they retain charge that has been applied to it. So this poses a risk in terms of you write a 1, and if you don't recharge that cell, over time, that 1 is going to become a 0, okay? So what happens is that in terms of design, RAM cells now include an extra circuitry for recharging, so that that cell is constantly refreshed to make sure that it maintains the data that has been persistent to it. So that obviously adds more complexity, that adds more delay, that even affects the power profile of your memory solution. Of course, it's still used. Why? Because it's more affordable, and there are more techniques which are actually incorporated to try and make it faster, especially by having multiple channels, which allows the processor to be able to at the same time, read or write to the same memory chip at the same time, because that improves the capacity, like the bandwidth, basically the amount of bytes that you can read or write at the same time to the memory chip. Okay, of course, it's used in your laptop. It's used in your graphics card. It's used in many modern devices that we have in use daily. So internally, this is how it is organized. You have a channel, a theme, a rank, a chip, a bank, a row, a column. One way, a simple way really of thinking of memory is to think of it as a matrix, okay? And obviously the matrix will have rows and columns. So where the rows and columns meet, where is it? Where the rows and columns meet, then you have a cell, okay? So a cell is like a basic unit of storage. That's where you can store a bit, 1 bit, either a 1 or a 0. So if you want to store maybe a byte, which is like 8 cells, then or you want to store an entire word, right? Then it means you have multiple cells involved. Okay, so basically, with the rows and the columns configuration, it means if you want to read from a specific address, you have to select the row, and then depending on the size of your memory, that entire row could be 32 bits or it could be 64 bits. Then you might want to only read a byte within that 32 bits. So you select those using the column decoders, okay, the column decoders. Or you want to, read an entire word from memory. So the column decoder will also specify that, okay, listen, select all the columns, within the selected row. So that's the idea really here. So you have the columns and rows, which together are composed into a bank, which is that smallest chip of like the smallest storage unit, comprising of columns and rows, which depending on the size of the DRAM chip you want to build or you are working with, then you can have those rows and columns, making up a bank, and then those multiple banks, being put into one chip to provide a certain capacity. Then the multiple chips, create a rank. So, for example, this side of the stick, with 8 chips, um, they give us rank 1, and then the other side with 8 chips also, they give us rank 2, and then you have your DIM, okay, being your DIM and your DIM, and it gives you multiple channels as well. It gives you multiple channels. Yeah, so this is the well, all right. So that was an overview of the architecture in terms of how it looks like internally, how the banks, form a chip, and a chip forms the rank, and then the rank forms multiple DIMMs, which can be accessed through multiple channels. So this is the same thing with a bit more finer detail. You can see rank 0 here, having multiple banks, and of course we said each bank will have multiple rows and columns, basically, to guarantee the capacity you want to provide for your RAM. Same thing here, a bit more close lookup. This is your 2 gigs DDR3 RAM, built from 8 128 megabytes chips, where each of them, from rank 1, they have multiple banks. For example, to have 128 megabyte, you need 16 megabytes times, right? And then to get to your 2 gigs, you need your 128 also times 8. That gives you 1 gig, and then for 1 rank you multiply it by 2, that gives you 2 gigs, from rank 0. right? So internally, you can see the row decoders and the column decoders, which we said are used to resolve and address into specific cells that you want to access within your matrix, depending on whether you want to read a word or you want to write to memory. But the arrangement is as we have discussed. So same thing, we can part it, sure it makes sense to you. We discussed this one as well in more detail, I mean, of the control, signals and lines which are used to either enable a particular row, and then you select a particular column, then you can read either a byte, a word from your memory by specifying, appropriate signals for the rows and the columns. Okay, so this is a diagram that really catalyzes what we have been discussing, the fact that you have a gap between your processor and your memory. The processor is fast, it's fast. It's faster than your memory. Of course, you can see the flattening here that started happening around 2002 or 3 or 4, when the improvement in the processor performance could no longer be simply realized by increasing the clock speed of your processor, because increasing the clock speed meant more heat was dissipated by your processor, because the heat dissipated by your processor is directly proportional to the clock frequency of your processor. So we hit what is often called here the power wall, right? The amount of power that was being dissipated by the processor was too much, and could not be handled economically using standard cooling solutions. So that's why we have that, flattening of the curve. Then a computer architect had to explore other approaches to, extracting performance from processors through exploring parallel computing, as opposed to simply, raising the frequency of the processor. But our interest, especially in this lecture, is the gap that we see here. Okay, we want memory to step up, step up as high as possible, so that we have fast computers. Okay, so SRAM, already we have discussed it, and also that it's built from flip-flops. Of course, you can see this one is making use of 2, 4, 6 transistors to make one SRAM cell. And the nice thing about it is that it's very fast. Okay, there's no need for refreshes, and it's also relatively easy to design. Okay, the only issue here is the cost. Okay, well, the main issue is the cost, and of course the issues of volatility, that for the transistors to be able to maintain the bits stored to them, they want power to remain supplied to their terminals. Once you remove the voltage, then they also lose the ability to retain the bit that has been stored in them. So SRAM technology used to build your registers, to your cache memory, and used also to build some faster RAM, static RAM, like static DRAM solutions are volatile and, and high cost. So because of speed, it is used in a number of high-end devices, including your routers, networking, including your printers for storage to persist data to be printed, and other high-end performance critical devices. So this is just a high-level overview of how the Core i7 CPU looks like, especially looking at the cache that it has, and how the cache is actually bent on the processor fabric. It's there on the IC of your Core i7, and it is shared by all the cores that make up your Core i7. So then you have the flash one, which is slower. As we have said, this is external one. There's your flash controller, which interfaces your flash memory to processor, to support reading and writing of data to flash. But the nice thing about it here is that it is non-volatile. So you write something to it, whether you remove the power or not, that data will be persistent. The challenge is that writes can wear out flash memory bit over time. So the more you write, delete, delete, then the memory bits can actually be tired, okay? And that can degrade the performance of your flash drive or your external flash disk. And the applications are there, your tablets, your phones, your personal laptops. Then we have your magnetic memory, which of course is the most cheap, gives you largest capacity at the cost of speed, So you have mechanical parts that are moving in the, that support persisting of data through magnetic fields. So that somewhat limits the performance of your magnetic memory. Optical, same group, very cheap, easy to get, large capacity at a low price, but you pay for that by slow speed. So let's end here, guys. Hopefully this is sufficient introduction that gives you an idea of what memory is, how it works, what are the candidate solutions that we have at our disposal. And then later we discuss how those can actually be cooked together into practical memory solutions we enjoy on our devices. Let's end here.